I'm very happy to be able to share with you online, with all of you, dear students. I will tell you a little bit of what the things that we do, the kind of things kind of mathematics that we do. And please let me encourage you to ask questions. So if you have questions and you just want to raise your hand, perhaps I can see you here in the chat also. You can just unmute your microphone and just speak up during the talk. Don't wait until the very end. If you have questions during the talk, please feel free to ask them. And I also open the chat. If anyone wants to ask questions, type questions, that's also fine. We can address them if I see them. So I want to tell you a bit of the kind of mathematics that we do. And the title that you can see here is Mathematical Modeling in Scientific Computing for Hard Electromechanics. So let me just tell you a little bit about me. I'm a mathematician. I work on numerical methods. We will see what those are. But basically, this is a subfield of computational mathematics. And we solve applied problems that come from real life applications. And in order to pass the information that that we give as an answer to the problem that we have at hand, we need a lot of mathematics. We need a lot of theoretical tools that tell us many things. If that passage is possible, if it makes sense, if the solutions that we're putting on the table for that problem, specific problem, is similar to the solution of the actual problem, and so on. But I'm just waving my arms here. Let's start. So I'm going to tell you what we do, and when I say we, I mean mathematicians or applied scientists on the same lines as Professor Yuri and Professor Vika work on. And then we're going to try to drive the discussion towards one specific application, which is the interaction between mechanical forces and electrical stimulus in the heart. So electrical stimulus drives the motion of the heart, and you know that that's what keeps you alive. So it's a very important system to understand. But before getting there, we're going to give a few examples of how we write down the kind of models that we use and how we solve them using simple cases. So what we do. So this is a field of numerical analysis, as I put here, and we use constructive methods to obtain solutions to problems. So if you ask me, let's compute the amount of gas inside of a chamber, or let's compute the amount of oxygen inside of this room, we can put all that data, all the information that we have there, and we construct a solution to that problem using tools that we're going to define in a minute. So the field of computational mathematics and numerical analysis and scientific computing also requires the person involved in that field to know at least a little bit about the physics or the biology or the population dynamics involved in the question at hand. Let's say that we want to give advice to the government as to how to manage the pandemic, the COVID pandemic. Because of the specific situation of the country where you are, the government decides to hire scientists, young, bright scientists as yourselves. So what kind of things we need to know? Well, we need to know at least a little bit of epidemiology, sorry. We need to know a little bit about infectious diseases and about how people react to pandemics. Right? So we need to know not just the branch of science where you are an expert, but you also need to know a little bit more in order to understand the language that the people who is asking the question speaks. So here I put that requires an advanced knowledge of the specific application, but even a little bit of that knowledge can get you very far. And in the specific example that I mentioned before of the interaction between the contraction of the heart and the electric stimulus, you need to know a little bit about physiology. You need to know what the heart is, what the function of the heart is. You need to know what the composition of the heart is, so a little bit of histology, right? And also what properties that material has. So that's material science, and particular biomechanics. And those things eventually talk among each other through the language of mathematics. So as you probably know already from the few things that you've seen in the university in terms of mathematics, it's not just about numbers. It's not just solving for x squared equals y. It's much more involved than that. It's, as I put it here, arithmetics and geometry, which are two branches of mathematics that deal with quantities and space, all the mathematics of space. That's geometry. And this is what we usually know in high school mathematics or first years of uni, but it goes much beyond that. It's about finding patterns, finding structure in nature. But even if we are not interested about applying these techniques or this theory to something concrete, there's just beauty in what we have in mathematics, in the theory of mathematics. So it's not only about models and applications, but also about the complication itself of mathematics and of the beauty of the theoretical elegance that this can bring. And also we work with rigorous deductions. So everything that we do follows specific line of thought. So we can trace our line of thought back and construct a theory. And this is a phrase used a lot in our field, that we said that we are machines that turn coffee into theorems, because we drink a lot of coffee and tea or whatever. But in general, what we do, mathematicians do, we pose problems and we try to give solutions to those problems. I mentioned here at the beginning that we are impure mathematicians, Vika, Yuri, and myself, in the sense that there is a distinction between pure mathematics and impure or applied mathematics. It's not very marked, but you can ask people and then they define themselves, mathematicians define themselves as applied or more theoretical or more pure mathematicians. So pure I think I put it here, yes. Mathematics becomes applied when it's used to solve real world problems. And you can have two approaches. So you can build a set of tools that you master, that you know very well, and then you are an expert in those kind of problems. So whenever you see a problem that resembles something that you know how to solve, you just go and apply the same techniques that you have, and then you basically are an expert in one tool, and then you just try to use that tool everywhere you can. So that's a valid approach. If you're a specialist in one kind of methodology, it's valuable that you use that for helping other people in solving their problems with your skill set. But another approach is that if someone gives you a problem, you just try to find any methodology, not necessarily the one that you're an expert, but some other methodology that allows you to give a solution, to give an answer to that question. And that's perhaps a much more difficult approach to science, but both approaches are necessary to make real advances in applied sciences. What I'm showing you here is a graph of a city. So these are points of major congestion in a network of roads. And this has been computed with mathematical models. And the kind of mathematical models used to describe this are very, very different to the kind of mathematical models that you would use to describe the currents in near Antarctica, right? So these are fluids that currents that that form around Antarctica because of the difference of temperature. Remember, do ask questions if you have them just by speaking up or by typing things on the chat. So what is it that I mean when I say models? Mathematical models are simplifications of our view of how the world works, how the world functions. Let's put again the example of giving a mathematical model for COVID-19. So here in Australia, every day the Prime Minister gives a speech about how we are progressing and how the mathematical models are predicting this, or that. So the impact of mathematical modeling is not just in the academic environment or engineering environment or in technology, but also in making decisions at the level of a country, right? To take a decision in terms of how the politics of health is going to proceed. So they are basing their decisions on predictions given by mathematical models. So those kind of predictions are the outcome of a group of people, a group of mathematicians, biologists, and scientists in general that have a view of how this pandemic works, and they put down in a set of equations, of formulas, of algorithms that are able to predict with a certain degree of accuracy what's going to happen in the near future with the pandemic. And each government is doing something different in that respect. But what they put on the table, that product, which is the mathematical model, is their view on how the situation works. It's not the reality because they just don't know all the details of how this pandemic works, but this is just their view, their impression on how this works. The thing is that once that you put down that list of concepts or algorithms or equations, you can work with that in a very precise way because those things are based on a precise language of mathematics. And as I try to explain here, there's a large element of compromise because you can decide to include some things that might be not important in the end, or you can decide to leave aside some factors that in the end were decisive in predicting some outcome. So it's a big commitment to say, I'm going to put these things into my model or not. For that, as much as you are informed on the topic, the applicative problem at hand, the better. So when do we use mathematical models? When we need to get insight and understanding, when we need to get predictions, as in the example of the COVID-19 pandemic that I just mentioned, and when we want to provide aid for people that take decisions. And something that is very useful in mathematical models is that they are very cheap because you can just test all the situations that you want very, very, very fast, and at least with a large variety of models in a very cheap manner. So you can test the effects of changes safely and cheaply. This has been going on for many, many decades. For instance, in the design of aircraft, they run simulations using mathematical models to improve the performance of planes, right? To improve the design of the materials that they use and the design of the shapes of the wings of the planes, and so on and so forth. Now, for the case of biology, I'm just going to check quickly on the time. Right. So, Yuri said that we can go over to the next session, right? So we can go over 45 minutes. In the specific case of life sciences, of mathematical models for biological systems, there are several ways of approach that. And you will see during the course of your studies the two options, because both are very useful and they are employed in different circumstances. So one of them is the so-called from scratch, where you go bottom up. So you start building all the elements that describe the phenomenon that you want to model, knowing every little detail. Let's put again the example of COVID-19. You put there the immune response of every person. You put there the economic factors. You put there because it's very relevant as well. You put there how people react when they see themselves in trouble. You put in there political decisions and so on. And then you try to combine those things, but you need to know how those interactions work in order to put that into a mathematical model. The key advantage of that is that you have a better understanding of all the mechanisms. You know what's going on inside of your model because you put the things that you master. You know how a mechanism works, and then you put that in your model. But there are other approaches where you just visualize the data, and that's the so-called top-bottom approach. And that functions pretty much as a black box. You don't know what is inside, you don't see what it does, but in some cases it works pretty well, because what it does is just mimics what the reality does without knowing why. And that could be very useful in cases where there's no way that you can write a model from scratch because you just don't know what the situation is. Let us transport ourselves back to several decades where people didn't have access to microscopic technologies that were able to tell you what happens at the atomic level. Now we know we can observe those things, but before we didn't. So we were trying to make models that were they were just their view on that, just because observing what the result is, observing the data, one makes a what's the word? Well, let's say a prediction on the outcome. So what we're going to focus on, at least in this talk, is this approach, the from scratch approach, and try to understand what the underlying mechanisms in the function of the heart can tell us about the overall structure. And the kind of models that we use, the kind of techniques that at least people in our field use, are based on so-called partial differential equations. And this is a very powerful way of writing mathematical models, but it's also limited in many, many cases. But we're going to leave out those limitations for the moment, and we're going to focus on the power that it has to actually describe many processes that we can observe at the macroscopic level, and sometimes also the microscopic level. And analytical solutions, so analytical techniques where you can write the solution with pen and paper of a given equation or a given set of equation, only occurs very rarely, only for very simplified problems and very simple geometries. You're able to simplify a lot the set of equations, and then you are able to solve that explicitly by hand, give a precise, exact solution. But most of the time that this is not the case. You need to give approximate solutions, and this gives rise to the field of computational mathematics. And even if you don't put those into a computer, you're still able to write ways of approximating exact solutions or analytical solutions, but now extended to more general domains, general shapes, general structures, right? Or general cases where you have more interaction between processes here and there. And for the kind of mathematics and applied mathematics that we do in this field, is very important that the solutions that we generate with these approximations maintain properties of the exact solution. So that's key. So the mathematical structure of the equations that we're working with also needs to translate into the approximate solutions that we have, and also the approximate solutions that we give that are copies or approximations of that exact solution that I would be able to write with pen and paper. They need to be relatable to the solution of the physical problem that we want to solve. So I can give a very beautiful picture of a population, of how virus spreads over a population, but if it's not informed or not in accordance with what the actual data of a specific country is, then that model is just useless, because we are not approaching at all what the actual scenario is. And that has been observed in some countries. So I have many friends in Switzerland, and they say that the government is saying, we just didn't know that this could happen. Our models that didn't say that, because they were thinking of other kind of scenarios where you work without the economic impact or things like that. But let's just come back to biology and to the motivating application. So what's the modeling cycle or pipeline? You observe what happens in your natural phenomenon. That can be a physical or biological problem in the case of this biophysics applications. And then you write a mathematical model. So mathematical model, remember we said, that is our understanding of what this physical or biological problem is. Once you have that mathematical problem in terms of equations, of algorithms, or of systems, we need to analyze that. See, does it make sense? Is it something that could eventually be solved, or is something that has no sense at all? Then we need to compute solutions to that, and that is what we call numerical solutions. I'm going to say what they are in a minute, and do analysis there. Then we can eventually compute results, generate results, and once we have those results, we need to see if they match with the expected outcome of a given model, right? So that's the step of validation and interpretation of our results. So we can see patterns here in this flower, and we can see patterns also in let's say art. Right. So I mentioned numerical approximation, but what's this? And here I'm plotting the numerical solution. It's a computational result of the velocity field in an aorta. So this is an aorta, and this is how the velocity occurs. I don't know if you can see well, but there's some recirculation there, implying that there's turbulence in the aorta. And some of these scenarios are important to analyze in pathological and physiological scenario. And you can see also pressure and so on. But this could be written as solutions of a partial differential equation, a system of partial differential equations. So these differential equations will tell you properties of the physical phenomenon. And those are physical principles of equilibrium, so mass conservation, continuity of linear momentum, angular momentum, things like that. And you can write those in general as finding the solutions of this equation here. I have a function f that is a function of that solution. And I also have some data, d, that's something that I give to the model. And I have a functional structure that tells me how data and the actual solution of the problem interact. And then this equals to something, for instance, 0. Okay, this is a general way of writing partial differential equation. The problem is, as we suggested before, in order to get exact solutions of this, I could only get far if I have a very simple geometry or a very simple functional relationship between f and u. If I go to something more complicated, there's no way I'm going to solve it. So the other thing is that if I want to pass this information to a computer to solve it approximately, only this very simple representation here requires an infinite amount of information. And this is very simple to understand. If I tell you that if I want to compute how this, where's the camera? I'm looking there, but that's my other screen. Camera is there. I should be waving hands there. So if I want to compute how this pen bends if I apply some force, right? That's just, I can describe this as an equation f of u d equals 0, where u is the displacement, f is the operator of, let's say, elasticity, plasticity, whatever, and I have data, which is the force that I am applying. And could I do that? Well, yes. What's the domain or the space where I want to solve things is the pen. How many points are in this pen that I could pass that information to the computer? So if you can try to count how many points you have there, you realize immediately this is a continuum. So there's infinite points here. My computer has, I don't know, like 8 gigabytes of RAM, I don't know, 8 or 16, but that's a lot, but it's not infinite. So there's no way I can put an infinite amount of information in a computer, my laptop or a bigger computer. So I need a way to transform an infinite amount of information into a finite amount of information. And this is done using numerical approximation methods. So we find an approximate solution, something that looks like that u, but is like UH, and that solves a problem that looks similar to this one, but is just not f, is FH, and the data is not d, is DH, and is equal to 0. The way that we construct that depends on what kind of methods you're working with, but at this point, let me tell you that you need to take, let me just go over one step, and let's come back to this later. Yeah, this is about the error. Let's just keep that. One of the methods that we use to do that, to pass information on an infinite dimensional object. Yeah.
Ricardo, excuse me, please. So we have 5 minutes before the break.
Yeah.
So if you want to continue, then after the finish of this 40 minutes, we shall re-log in again to the second session. Okay.
Okay.
And,
so I could continue, but just let me know.
Okay. And one more announcement in Russian. There will be recording for students. They will send their names to chat. Don't worry, this is not about you, this is about us. We just check their presence, okay?
No problem.
Студенты, пожалуйста, присылайте сейчас ваши фамилии и группы. Please, Ricardo, proceed.
Okay. Okay, since we're going to do a break anyhow, let me just go back and talk about that after the break. So if I'm taking an infinite amount of information and I pass it into a finite amount of information, of course I'm going to incur in some error. And this error is of several types. You're committing error the moment that you write a mathematical model as well, because you're doing simplifications of real life. So there's one error there, but also when you pass that equation to the computer, you're committing error. So there's discretization error, where you translate your mathematical problem into a finite dimensional one that you could solve in a computer. And there's an approximation error. And what we do also in this field of numerical analysis is to control that error, to know how big it is and how we can make it smaller, using more points, right? Using larger computers to have more computational power, but not just only that. There are other techniques as well. Another thing is that we need to take into account the governing principles. So if I am trying to solve principles that look like this, my numerical solutions, my approximate solutions, should also behave in this manner. Okay, before the break, I'm going to give you the first example of heat distribution. So this is the heat map of a phase, and we can compute that, the heat map phase, even without taking a photography, by solving an equation. So I can solve the heat equation, which is written here. That's the equation. These are the conditions that you impose on parts of the boundary. And an application of solving the heat equation, how to compute a thermal map, are, for instance, in the eye. So this is a mesh for the eye globe. And why is temperature mentioned here? Because outside of the eye, in the cornea, in this area, you are exposed to the ambient temperature, which is 0 degrees, -20, -40. I don't know what's the minimum in Moscow you can get, but it's quite low. And inside you have, around here, the nerves, you have the body temperature of 37 degrees. So you have a temperature gradient which is really, really high. And inside of this eyeball, you have liquid, you have aqueous humor. And whenever you have liquid and you have changes of temperature because of energy conservation, you do have changes in the flow there. So you could have problems in your vision whenever you have large gradients of temperature. And this is one simulation when we see the temperature in the cornea there. How do you get from the equations of thermal maps to actually solve them in the computer? So key to that was this person here, born in the times of the Russian Empire, where he proposed a method around 100 years ago, and it's still being used in today. It's a very powerful technique on which we base all our development so far. And it tells you that you can represent infinite dimensional quantities as just matrix systems. So you can rewrite this set of equations just as a matrix system that you will know already how to solve, at least for small matrices, in your linear algebra courses. So the passage from that to that has very elegant mathematics, very complicated mathematics, and very powerful techniques that ramificate to different branches of mathematics. So partial differential equations, functional analysis, approximation theory, and many other branches. Okay, let's stop here, and we rejoin in the other link. So I kept the chat open in case anyone wants to jump in and ask questions. Good. So here we have another example of, I hope you can see that, how we have flow going into this part of the domain, and what we are showing here with this tissue that like flying is these are the concentrations of chemical substances in a flow. So we have a flow, let's say an artery, and those colors will tell you whenever specific chemical concentration is high or low. Other examples where we use the same kind of methodology of Boris-Galerkin to pass partial differential equations to approximate solutions is when we compute, for instance, the flow past an airfoil. So perhaps you can see there. Yes, you can see the velocity magnitude around the wing here, and you can see the turbulence forming just beneath the wing. We can also see something similar set of equations that you can observe whenever you have a landing gear. But all this is based on the same idea of Boris-Galerkin. We have, in the case of the modeling of the cardiac function, very complicated set of equations, because you have many systems that interact together to eventually get the muscle to pump blood out of the ventricle. And even a simplification of that is already a big set of partial differential equations, as the one we can see here. Perhaps I'll tell you how one arrives to a representation like this. So these are all the components that are participating in the construction of the model. So there's no way that we can solve this exactly. We need approximation techniques, and this is simply too difficult. So how that model comes into place? First of all, why do we need to provide a model for the cardiac function? Well, first, just curiosity, right? We can have a better understanding of how our body works if we try to give a description on the components of certain parts of the physiology. But it can also help in applying diagnostic measures, and in particular in the group of URI, they have been putting a lot of effort in understanding physiological and pathological conditions of the heart, and into putting mathematical models to use. So real use. They talk every day with physicians, they talk every day with clinicians to improve the way that we address medical sciences for the heart. So we can assist the medical prognosis, we can plan treatment scenarios and so on. But it's very difficult, first of all, because we have different systems that interact. I only mentioned two here, which is the mechanics, right, the deformation, elastic deformations, and the electric stimulus. These two very different systems, they interact closely, not only at the visible level, but also a very small level, intracellular level. We will see that in a second. And the other issue is that most of the evidence cannot be obtained from dead tissue. Many of these processes occur because we are in a living body, because we have life in the cells themselves. So even the ways that we address to describe equations for this are still under development. So there's still a lot of things to understand There's still a lot of things to do. And that's also one of the main messages here. So we are way behind in the full understanding of the processes, for instance, of the heart. We still need people like yourselves with ambition, with drive to create more models, to advance science in that respect. Why do we need to incorporate several physical phenomena? Why can you just keep with one single thing, just looking at the, let's say, electric stimulus, and that's it, I don't need to worry about anything else? Well, because there are pathologies where you do have a close interaction between those two things, and if you separate them, and if you try to understand a global phenomenon just by looking at one physical system, there's no way you can describe what occurs. So you do need integration at some extent to the properties of the heart. So some of those things are resynchronization therapy, and there are diseases like hypertrophies where you do have not just one single system working, but several that interact together. And I have put some other examples here. This is scar tissue where the passage of electric potential is impaired, and also the contractivity of the tissue is impaired in that region. And the heart is not isolated, of course. You also have interaction with the cardiovascular system, and that also needs to be taken into account in the modeling formalism. But as I mentioned before, we have processes that interact together, not only at the visible scale, like the body of the organ, but also smaller scales in space. You have the tissue at the tissue level, at the cell level, and at the intracellular level, you have interactions between several multi-systems. And this occurs also in several time scales. You have diseases that take years, right, to develop, and metabolic response a little bit faster. The cardiac cycle is the order of 1 second. But then you have also other things that occur where you have chemical reactions, for instance, fast calcium waves that are on timescales much, much smaller than the timescales of the disease itself. And at some point, at some extent, at some level, you want to make the connection between the timescales too. So you realize that you have a very complicated issue, not just because you have several space scales and time scales, but also because you have multi-physics. And you also have, this is a simplification of the tissue. That's how we represent the tissue from images, from medical images. We're able to describe it like that. And the tissue has structures like fibers, and those fibers, they have specific properties, mechanical properties, and we want to incorporate those properties in the modeling that we do as well. And if we zoom in, we observe that in those fibers, there are cells, and those cells have a specific alignment. And not only cells, but we also have network of some tissue outside of the cells and some other kinds of entities that produce collagen. That's at the mechanical level. At the electrical level, if you assume that you have a cell and you have inside of the cell, you have mechanisms that, because of electrical stimulus, make that some channels in the cell will open and close, and they allow some ionic quantities to pass from one side of the cell wall to the other side. And that eventually generates an imbalance in chemical quantities that will produce motion at the intracellular level. And this is specified here. So this is a cell. Inside of the cell, we have another kind of structures, and those structures will start to contract whenever you have more calcium inside of the cell. And calcium is inside of the cell, because there's more calcium going on around once you do have an electrical stimulus. And so you observe that this is a cycle occurring very rapidly inside of the cell, and eventually that interaction propagates to larger scales, eventually to make the tissue contract. So we have at least 4 subsystems. One is the electric activity, the electrical impulses. You have also deformations, because you have elasticity, right? This is what basically connects these 2 systems, the mechanical activation. And you also have the fluid dynamics, because you have blood inside of the ventricles that is eventually pumped out to the rest of the body. So those are the connecting dots in your model, and all of those components in your model are solved using these numerical methods. And in order to get there, the same pipeline that we use for the heat equation, for the thermal description of the face of a person, are used here, right? So we put on the table what we think the reality is on this, or on that, or on this other process. Then we analyze that. Then we write down a set of equations that are passed to the computer using advanced mathematics of approximation theory and so on. And then we need to do validation as well. I will give you just a couple of more examples. We can also model the contraction of cells. If I just have a cell, these are cardiac cells, but you can just work on other types of cells, embryonic cells, skin cells, and see how the mechanical properties in those cells interacts with the release of calcium inside of the cell, and solve those problems using numerical methods. These are also representations of idealized ventricles. So I have ventricles, and depending on the activation, this means the interaction between contraction and electrical stimulus, I have different patterns of contraction. And how do we get to those kind of things where we have geometries that are coming from CT scans? So we have medical images. From those, we generate geometries, computational geometries, that can be rescaled, smoothed out, and then we create these so-called meshes, which are computational structures that represent space for the solid, which is the tissue itself, but also for the compartment where fluid is going to be. And those steps are done also using numerical techniques. All those steps, even the generation of those fibers. And eventually we can get results like that. So that is the contraction of a biventricular geometry. So you have the left ventricle, the right ventricle, and what we are observing here is the electric potential, how that propagates through the tissue, and how the contraction occurs. So these are the magnitude of displacements, so how much the deformation you observe in the tissue. And then you see that you have the expected behavior on a physiological heart. You can also study what happens when you have pathologies, and how can you treat those pathologies using drugs or using procedures. But before trying on patient, you can try it on a computer, which can save lives. Okay, I'm going to finish. I'm going to wrap up. The take-home message is an example of electromechanics of the heart, and it involves concepts such as elasticity, diffusion, fluid dynamics, chemical reactions. And for this system, as well as for other systems in biology, you have many equations. And those are strongly coupled, very nonlinear, and very difficult to solve by hand, impossible to solve by hand. So we need numerical techniques, approximation techniques. And as we advance in this area, problems get more and more complicated. So we need more and more sophisticated techniques, sophisticated numerical methods, state-of-the-art numerical methods. And there's plenty of things that we still don't know about the mathematics of this, about the biology of that, about the physics of this, and how we couple things together. One of the questions is, how do we ensure that after coupling the sub-problems, or if I know how to solve each of those separate systems, what happens if I put them together? Am I confident that the solution that we produce is going to be similar to the one from the physical problem? So that also is related to the concept of validation. We're still far from validating a full model for the heart, but there are advancements in many subsystems, and nowadays you can find very sophisticated methods that are validated, at least for some pathological cases. And eventually, what we would like is to deliver answers that are clinically relevant. And this is a very strong point in Uri's group, because they work hand to hand with clinicians, and so stick to them, follow what they do, because there's a lot of potential for obtaining great results when you talk directly with clinicians. But you do need an understanding of the numerical techniques. You do need an understanding of the underlying physical phenomena, and how you put those things together to build up a consistent model, a model that can give you something feasible. All right, thank you very much for your attention. And if you have any questions, I will be glad to try answer them. If you do have questions and you don't want to make them publicly here, just send me an email. That's my website, not my email, but my email is ricardo.ruizbaier@monash.edu. Just send me an email if you need more information about this, or just ask Uri. He can point you towards me. Thank you again.
Thank you very much, Ricardo. I